ask everybody, I'm going to ask everybody if you can keep your microphones off, that would be great. And we'll save the questions till the end. At the end, we'll have a question and answer session that Boris can answer any questions that anybody has. But we're very pleased to have Boris talking to us for our next talk. And I'm going to, can you put up your slides, Boris?
Yeah, sure. Just let me make down some stuff. So that's okay. Here we go. All right, and let me make how to make this full screen. Just and then see all tools. No, okay. Is it okay? Good size?
Yeah, seems to be fine. Yeah.
Okay, because I don't see something is screen. I cannot make full screen. Okay. So that's oh, maybe if I clean, this is full screen. No. Anyway, okay. I'm very happy to be part of this World Zoom Congress on No Theory dedicated to 80th birthday of Will Kaufman, and I'm so happy that I'm gonna be not alone with two or more dimensional nodes. So which means knotted spheres of dimension n in the sphere of dimension n+2. So for simplicity, I will consider a situation when you have two-dimensional nodes in four-dimensional sphere. And this is not just that. I would like to explore what's connection between nodes and action of discrete groups, especially for hyperbolic lattices. If we imagine, you may have standard round sphere as the boundary at infinity of a hyperbolic three-dimensional space. And in this real hyperbolic three-dimensional space, you have action of uniform hyperbolic lattice. Uniform means that it is co-compact. And but you would like to make deformations of such actions. And this is related to Teichmüller theory, how you can consider different discrete representations of a given discrete group, say hyperbolic discrete group of isometries. And when you're talking about dimension 3 or higher negatively curved manifold, say symmetric spaces rank 1, then you face rigidity. And this rigidity of deformation, which is came after works by most of Margulis and other people, and it says that if you have closed or finite volume hyperbolic real or complex or quaternionic or Kelly hyperbolic manifold, then homotopy equivalence of two such manifolds implies isometry of that. So in that sense, if you consider Teichmüller space as space of different Riemann metrics, hyperbolic metrics on a manifold, then this space just collapses into a single point. So therefore, there are no non-trivial deformations of hyperbolic structure. However, if you look back to Teichmüller space, it was originated after works of Teichmüller and especially Lippmann Beers and Lars Alfors, then you look at Riemann surfaces, you look at conformal structure on Riemann surfaces, and you would like, of course, you may consider conformal structures induced by hyperbolic metric on this surface, but you may consider deformation of this surface in the sense of conformal flat conformal structure. So in that sense, for surfaces, these two approaches are isomorphic. So Teichmüller spaces are the same, but in dimension higher than 2, already in a 3-dimensional hyperbolic manifold, we see that one approach with hyperbolic metrics is degenerates. So Teichmüller space degenerates into a point. But if you consider deformations as deformation of conformally flat structure, which is induced by hyperbolic metric, then such conformally flat structures create big Teichmüller space, and that was kind of my pioneering work. This was some Stony Brook conference in the 70s, I believe 1978, when I published a paper and published in the proceedings in a Princeton advanced study series. So that's and that's what I would like to explore, how we can deform action of uniform hyperbolic lattice on n-dimensional sphere at infinity of hyperbolic space where this group, this lattice, uniform lattice is acting. How we can deform in the sense of conformally flat deformations and to push this action to be action not on a round sphere at infinity of hyperbolic space, but action of discrete action on some 2-dimensional node or n minus 2-dimensional node, noting inside of n-dimensional sphere. So in dimension 2, or say 3-dimensional manifold, or lattices, we are talking about knotting of 2-dimensional sphere inside of 4-dimensional sphere. That's the simplest case. So, and not just that, we would like to make such deformation that such discrete action on such node, hopefully non-trivial node, 2-dimensional node or higher dimensional node, but that this action should be still ergodic action, and even sphere itself metrically is knotted sphere, knotted, so non-trivial node, would be metrically nice. It's kind of trace of quasi-conformal mapping, or in analysis it's called quasisymmetric mapping. Therefore, we're looking at the situation when we embed 2-dimensional sphere by quasi-symmetric embedding into 4-dimensional sphere and still have action on this node we obtain. And this action is equivariant with respect to original action of the uniform hyperbolic lattice we started with. So that's the main idea of my talk, and I will use for this to demonstrate how it works. My recently introduced notion of conformal interbreeding of manifolds, conformally flat manifold. And this conformal interbreeding is kind of generalization of famous Gromov, Misha Gromov and Ilya Petetsky-Shapiro, so-called hyperbolic interbreeding. They were using this hyperbolic interbreeding to demonstrate that there are non-arithmetic lattices in all hyperbolic spaces, no matter what dimension it is. So, and the idea was, okay, I will talk about a little later more on this. So that's, and I just used this opportunity. So if somebody is interested in this stuff, so I recommend to take a look at a new published book. Just last summer, I published in De Gruyter in Germany, my new book with title Dynamics of Discrete Group Action. So that's was in series Advanced Analysis and Geometry by De Gruyter. So that's you can see many details there. So I will start with first time when such nodes, such knotted two-dimensional spheres appears with respect to discrete group action. So this happened as a kind of side result of my and Andrei Titenov work on non-trivial homology hyperbolic cobordism. So, and this was work. It was published in 1986. You see, like who knows where, when in the Journal of Differential Geometry. And this was quite a surprise that that's all possible to have four-dimensional cobordism, which is compact manifold with boundary, consisting of two components. And inside of this compact manifold, it's possible to introduce complete hyperbolic metric of constant negative curvature. Therefore, it is hyperbolic, locally hyperbolic metric. And if you look at homology properties of this cobordism, then relative homology groups of one component and the second component are trivial. So in that sense, cobordism is homology cobordism, but it is not trivial in the sense that it is not looking like product of one boundary component by closed interval. So, and appears to be that if you consider universal cover of one component of this cobordism, then universal cover of one component is the discontinuity set of group. Actually, it is isomorphic to hyperbolic uniform lattice. And another component of the same cobordism, the same boundary, second boundary of hyperbolic manifold with boundary, is the complement, is covered by the complement of wild, closed, wildly noted everywhere three-dimensional ball. Therefore, we have embedding of three-dimensional ball into three-dimensional sphere, such that the boundary sphere is embedded as a wild sphere, and this wild sphere is widely noted at the, in some dense subset of this sphere, wild sphere. So, and you see like a picture of such wild knotting. You may imagine that first you have, say, knotting, wild knotting, actually periodic wild knotting, coming down to limit point, say, at the origin. And the same knotting goes up to infinity, and knotting and knotting. And by the way, since you have ergodic action of the group on the original sphere, round sphere, the boundary of hyperbolic space, then you have that, now you have such ergodic action on the boundary of this ball. And the boundary of this ball is just the limit set of discrete representation of your hyperbolic lattice. And the image of this discrete representation now is discrete isometry group, but not of three-dimensional space, but four-dimensional hyperbolic space. Therefore, you have such discrete representation, faithful discrete representation, and the limit set of this representation is such wildly noted sphere, widely again noted at everywhere on the boundary of this ball. So this first time when we just faced such wild two-dimensional sphere with action of hyperbolic, uniform hyperbolic lattice. So, and appears to be that such cobordisms, such behavior is very natural, and we proved with Titenov that condition that action of a Kleinian group in any dimension convex co-compact, and with one invariant contractible component of discontinuous set at infinity of this hyperbolic space, then you get compact Kleinian manifold where boundary is the quotient of discontinuity set at infinity by the action of the group. And you have that you obtain n-dimensional, n+1 dimensional cobordism, and the triple is a homology cobordism. So, and actually, if you add additional condition, not only that one component is contractible, invariant contractible component, but if you have two invariant contractible components, then it will guarantee that this will be the full discontinuity set, and the n+1 dimensional hyperbolic cobordism will be homotopically trivial in the sense it will be H cobordism. So there are lots of play here, possible play along all these conjectures about how to describe such cobordisms. But you know that in dimension 4, such invariants for triviality of cobordism are not working, and four-dimensional case is very special. So that's okay. Now, when we constructed such homology cobordisms, this was used some idea, my old idea, it's so-called block building construction, that you may consider hyperbolic blocks, and which means you have some part of hyperbolic space, and you have this part to call it as a block, and then this block can be deformed in a good shape. Like if you are in the dimension 3, you may think that okay, we consider this contractible block as a cube or a hexagonal prism or something like this. What's important that you have very strong, very precise control over geometric properties of this block. And then you may construct some configuration, topological configuration, whatever it's in your mind, what you would like to create. And you may, for example, take any periodic Fox-Artin arc, and then to make thickening of this Fox-Artin arc, wild, non-trivial arc, which means the complement of this arc has non-trivial fundamental group. It's not like arc in three-dimensional space, like segment. It has trivial complement. So therefore, you start with such non-trivial wild Fox-Artin arc, periodic, and then you thickening this by making this thickening like a sausage around this arc. You have it as union of balls. And in each of balls, you have some action of hyperbolic group, because in round ball, you may introduce constant curvature, negative curvature metric. So you may consider conformal model of a three-dimensional hyperbolic space. So therefore, you now have such configuration of balls, and by using combinatorial group theory, you can use standard procedures like amalgamated free product or H&N extension of groups acting in each of those balls. And in that way, you may create action of uniform hyperbolic lattice, now acting not in three-dimensional hyperbolic space, but acting in four-dimensional hyperbolic space, and at the infinity three-dimensional sphere. It works in a way that limit set would be such a wild two-dimensional sphere inside of three-dimensional sphere. Okay, so and especially this way that I'm dealing from the beginning with hyperbolic blocks. I glue them together by hyperbolic isometries. Therefore, I create big uniform hyperbolic lattice from subgroups of these lattice. And gluing is along totally geodesic sides. It's precisely what Gromov and Petetsky-Shapiro did for hyperbolic interbreeding. So for gluing is done by hyperbolic isometries. So, and in that way, they were able to glue non-commensurable groups, lattices. So in that way, in each dimension, they were creating as a combination of two non-commensurable lattices, non-arithmetic lattice. So, but this is away from what we do here. So therefore, we have such construction, and we observe, yes, the limit set is two-dimensional, widely noted sphere in three-dimensional space. However, this wildly noted sphere has nerve of knotting one-dimensional nerve. So in that sense, if you consider this nerve of knotting, this non-trivial Fox-Artin arc is not noted if you are in four-dimensional sphere. In that sense, it shows that the two-dimensional widely noted sphere in three-dimensional sphere, now it is part of four-dimensional sphere. But in four-dimensional sphere, this widely noted sphere is a trivial two-dimensional knot. So in two-dimensional knot is what? It is just embedding of two-dimensional sphere into four-dimensional sphere. And then we see whether this knot is trivial or not trivial. Like, can you deform it to round sphere or not? So that's, but another side of this block building construction, what I used, was the fact that I used for deformation quasi-conformal mappings. It's so-called bending deformations of hyperbolic manifold. So it's like you have codimension one totally geodesic surface in your hyperbolic manifold. And now you bend your manifold along this totally geodesic hyper surface. It's like, imagine you have a plane and you have two-dimensional plane in three space. You have a line. Then you may bend this plane by rotating half of plane along this line. Therefore, after that, you do, instead of plane, you have just dihedral angle. So that's what the procedure of bending. This procedure of bending can be described very much analytically. And so that's, you can make this bending compatible with action of discrete group. So in that way, you will arrive at the procedure I used long ago when I showed that the Teichmüller space of conformal, flat conformal structures is not trivial. So I use such type of deformations. Later, the Thurston used the same idea to show famous Mickey Mouse example deformation. So that's for surfaces. Okay, so in that way, using such quasi-conformal metric controlled deformations, you see that what you obtain if you restrict action of your lattice to the sphere at infinity, then there you have now a mapping, embedding of this two-dimensional sphere into into three-dimensional sphere at this time. And this embedding is quasi-symmetric embedding, good in metrical sense. I don't want to go along the way. So, but since the nerve of knotting of that two-dimensional sphere in three-dimensional sphere and in four is one-dimensional. So therefore, two-dimensional, while two-dimensional sphere is trivial two-dimensional knot in four-dimensional sphere. So, but there are many ways to create non-trivial two knots in four sphere, or n minus two-dimensional knots in n sphere. So you can use ribbon knots, ribbon n minus two-dimensional knots, or say two knots, the same way as ribbon knots used for one-dimensional knots. Or you can use span two knots. They are creating two knots from initial one knot in three space, in three sphere. So, and actually they are ribbon two knots as well, or suspension two knots from one knot. So, but here in that picture, what I show is example as a ribbon two knot with M fusions, and it goes in a way that you have, say, the base sphere is not two-dimensional sphere in four sphere, and you make a disk removed from that sphere, and now you start to glue to this boundary of removed disk, the circle. You glue to this boundary a cylinder, and you make this cylinder which goes in linking another sphere, the second sphere, and this link is done, then it goes back to the base sphere and linking this sphere again, and so on and so on. And finally, this second end of this cylinder is glued to the second sphere. The result, in the sense of intrinsic topology, is still two-dimensional sphere. So, and you can make it not with two original spheres, but with any number, say, number of them is called M fusions. So we will consider to illustrate how we do such non-trivial two knots with hyperbolic lattices ergodic action. I would like to consider the simplest situation to illustrate. I will first approximate, you see, like what here we have spheres and cylinders. Now imagine that you approximate these spheres and cylinders in PL category. In PL category, and you make cylinder as union of some, polygons and so on. Or even better to say, you may think that you have a sequence where instead of these cylinders, you're thinking about union of balls intersecting consequently each other, and therefore boundary of union of these balls create cylinder. So that's what cylinder. But now instead of balls, I would like to take not balls, but say cubes, or some prisms you may use, three-dimensional prisms, and with controlled sides of this polyhedra. For example, these cubes. We would like to have a control on size, and we will cover this, say, two-dimensional boundary, two-dimensional sphere with a set of balls whose boundaries intersect each other by rational angles. Therefore, I would like to put kind of action of hyperbolic uniform hyperbolic lattice inside of this cube. So, and we will make some connection between size of cubes or original spheres we are linking by cylinder, and size of cylinders which are linking them. So you see, you start with first cube. This is a three-dimensional Euclidean subspace plane in four-dimensional Euclidean space. Then you take on the side of this cube little square, and you glue to this little square cylinder I'm talking about before, this cylinder will link another cube representing another sphere, two sphere. So, and this cylinder will be union of little cubes, one cube, another cube, another cube. And you see how these sizes, very important, how sizes of these cubes related to each other. You see, here I show a square side of big cube. And then you have 4 balls centered at the vertex of this square, and they have intersection of boundary spheres as pi over 3. So then they not cover the whole square, but I cannot for more balls, and again it will be still some window not covered by those balls. But now if you consider intersection points of circles on the surface of this square, you see that you have little square inside of this big square. So therefore, the size of this little square indicates the size of these cylinders as the union of these cubes, which are linking big cubes, big spheres. So, and therefore, now, as I said, inside of each this small or big cube, we have somehow defining action of discrete group, and we combine this action together to create a big hyperbolic lattice by using Gromov-Petetsky-Shapiro interbreeding construction. So, and since we now have representation, we now have this picture in a 4-dimensional sphere or 4-dimensional Euclidean space, we will use conformal interbreeding instead of what Petetsky-Shapiro and Misha Gromov were working, gluing sides of hyperbolic polyhedra. Now I will use gluing of conformally flat gluing of sides of conformal polyhedra. They are kind of parts of spheres, round spheres. And you see, that's interbreeding construction is working very well. It needs kind of combination theorems like Bernard Maskind introduced in dimension 2 combination theorems. It is kind of adaptation from combinatorial group theory, amalgamated free products and H&N extension. Now it is adopted to action either in the hyperbolic spaces or in groups consisting of Möbius transformations. So that's possible to, or even more. So that's so-called combination groups. How from 2 discrete groups to combine new group, which has original groups as subgroups and still working discretely in the space you are working in. So that's a technique together with my standard blocks or block building construction has several applications. Like I said, in homology, cobordism, creation not faithful discrete representation with arbitrarily large kernel, which is very handy to prove some old standing conjecture in classic analysis, geometric analysis. Or now I'm using it for wild 2 nodes in 4 sphere. So for what we now have is result of this all constructions as a theorem. So we start with a given non-trivial ribbon 2 node, any. Then we approximate PL approximation of this 2 node, and then we start to build a hyperbolic lattice. This hyperbolic lattice is uniform hyperbolic lattice in three-dimensional hyperbolic space. However, we consider discrete faithful representation of this lattice gamma into isometries of five-dimensional hyperbolic, real hyperbolic space. Therefore, now we have action of this three-dimensional hyperbolic lattice into five-dimensional hyperbolic space. And you have also action of this lattice at infinity of those spaces, like two-dimensional sphere and four-dimensional sphere. So then we have now the image as the Kleinian group. It is a discrete subgroup of isometries of five-dimensional hyperbolic space. And this discrete subgroup acts ergodically on its limit set. And limit set is everywhere while to naught, k infinity. This while to naught k infinity is somehow obtained from initial given naught k. So this k infinity naught is obtained from k as infinite compounding. And moreover, the everywhere while to naught k infinity we create as the discontinuity, the limit set of our discrete group action G. This to naught is the image of quasisymmetric gamma equivariant embedding of two-dimensional sphere into four-dimensional sphere. So here we have kind of advantage to use knot theory and invariance well known in knot theory to prove that what we obtain not going to be trivial knot like what we had trivial two-dimensional wild sphere, which is in the sense of knot in the four-dimensional sphere is trivial knot. But here we can prove that the knot we construct in that way, which is invariant for G action, will be not trivial two-dimensional knot in four sphere. So that's we use again our conformal interbreeding construction, and you see what we have to address very touchy question, non-triviality of the knot we obtain. So non-triviality of this mu knot with invariant for discrete action. We use Alexander duality. So in a way that we can prove that we consider the complement of this knot. And the complement of this knot is discontinuity set of our group G action. So then this discontinuity set or the complement of knot k infinity has infinite cyclic covering space, omega hat. And we now may consider its Alexander invariant. It is homology groups of omega hat of our wild to naught k infinity. And by using Meyer-Vietoris exact sequences, we prove that this Alexander invariant is not trivial, therefore our knot is not trivial, period. So that's probably, I should stop, it's precisely 40 minutes. So like, and here you can see some references I used. That's first paper about non-triviality of Teichmüller space of flat conformal structures on hyperbolic, say, manifolds of dimension 3 or higher. Then about non-trivial cobordism and some other, so like two last books on conformal geometry and on dynamics of discrete group action. And there are more like applications of this in different ways, in geometric analysis, solving some well-known problems in geometric analysis, like Pierre Fatou problem about radial limits for quasi-regular transformation mappings and so on and so on. So that's all.
Great.
I stop here.
Thank you, Boris. That was great. Thank you very much. Let me stop the recording here. And